Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do thermal sharpening using modest data in Google Earth Engine platform and Python API programming. As you can see, in this tutorial, we're going to use the NDVI product to increase the spatial detail in thermal infrared bands, LSD specifically, from 1000 meter to 250 meter. This tutorial is really helpful for those of you who are interested to know more about the downscaling procedure in the remote sensing. So, make a new notebook in the Colab environment and let's call the essential libraries in the first step. Start with Earth Engine libraries. Import Earth Engine library, then GEE map, and then Xarray as XR. The Xarray allowing us to actually convert the image collection to the multi-dimensional array structure, and then we can easily apply uh, some sort of machine learning algorithm or Python tools easily. So just remember that we can do this conversion by integrating between Xarray and Google Earth Engine functions that is offered by XEE tools, meaning that in addition to the current libraries, we need to have the XEE library. So let's install the XEE because the XEE is not built-in library in the Colab environment, and it is necessary to install it before doing further analysis. So then import XEE. As you can see, after a few moments, the XEE installed successfully and without any challenge. In the next step, we need to make a bridge between Earth Engine and Colab environment through the Earth Engine authentication functions. Earth Engine.authenticate and then initialize Earth Engine accounts. Enter your project name. If you want to know what is your project name, go to the code editor environment, upper right, you can find your account information. Go to project info and copy and paste the cloud project into your code. Every one of you has a specific, actually the cloud project that made a connection between Earth Engine account and your Google account. So the next argument is OPT URL. The OPT URL, you can find it in a GitHub page available for XEE. Just open a new browser, open a new page in your browser and type Google Earth Engine XEE like this. And then one of the links, it's about one of the results is about Xarray extension for Google Earth Engine. If you go to the address, then you will face with a detailed instruction about XEE, where you can find the OPT URL here. Just copy and paste it. Then run the code. Sounds something is wrong about the authentication. There is a typo mistake here. Yes. Now Colab asks for permission to make a connection between Earth Engine and Colab environment. Now you can grant the permission by clicking on your account information. Then click on continue. From now on, you can use Earth Engine script in the Python environment. That is really helpful to use the Earth Engine capabilities in the Python environment. So, in the next step, I need to define the region of the interest. So, make a new variable map from GEE map called the map function. the map function allowing us to make a user interface with the satellite background that allows you to select your region of interest using the drawing tools. Set the base map to the satellite. Let's print the map again. After a few moments, you can see a user interface to select your region of interest. So, seems something is wrong because I need to have the satellite background. Let's write the base map again and run a code. After a few moments, you can see a new user interface, a map interface with a satellite background. You can use this tutorial for all around the world, no matter where is your region of interest. You can use this tutorial, this code, and satellite data for whole of the world. As I'm an Iranian user, actually I prefer to select a region in my own country where actually farmlands also available. So my region of interest located in the southwest of Iran, where you can see a wide actually area, a big area actually allocated to agricultural activities. Okay, then I need to actually select a part of this region as the region of interest through the drawing tools available here. I'm selecting this area. There it is. So in the next step, I need to have the rectangle as a variable. The selected rectangle must be utilized or must be available as a variable into code for the further analysis because we need to bound our analysis to the drawed region. So from the map, select the draw area. Last feature, convert it to a geometry and let's print to make sure the rectangle created. Everything is fine. In the next step, we need to call MODIS thermal infrared images. Go to the code editor, throw the search places and dataset, type MODIS temperature product here. Various MODIS temperature products available here. I prefer to use one of the multi-temporal products with 8 days frequency. There it is. Such dataset, the multi-temporal, the dataset actually produced by a period of time or aggregated in a period of time always offer a better quality with a less uncertainties and less affected by the cloud cover. So let's copy the collection snippet and paste it. Let me back to the code then. So there it is. A new variable as LSD created, image LSD called here, as we already utilized actually the Earth Engine libraries. The Earth Engine image collection is readable in the Python environment. So now I'm gonna actually make a filter or filter out the data for a period of time. For example, I need to make an average LSD image for 2021, one single image. It is easy to address the downscaling procedure on one single image. It is easily understandable for the users. In the next tutorial, I will show you how to do this for the time series analysis too. Okay, filter date, select the target band. It is LSD day with 1 kilometer spatial resolution. If you go to the data characteristic bands here, you can find the band information such as the band name and a scale factor. I want to make an average image for whole of the year using .min function, and then I need to apply the scale factor that is 0.02 as mentioned here. So The unit of measurement is based on Kelvin, but I need to convert it to degrees Celsius. That subtract 273 and 15. There it is. Okay, let me to make a bigger space here and LSC created. Then I want to have a higher resolution image for a same period of time that highlights the spatial detail in this area. Here it is the NDVI. As I'm working on agricultural area, the NDVI is really beneficial and allowing me to have more detailed about the farmlands and sectors. Okay, now go for MODIS NDVI product. MODIS Terra vegetation indices with 250 meter is also available. You can see, just copy the collection snippet and paste it into your code and filter it to the same period of time, 2020, 2021. Select the target bands. Go to the band and select the NDVI. As you can see, calculate the average of each pixel in 2020 and then multiply to the scale factor already addressed here. So that's multiply to the scale factor. There it is. Now two single image provided. One of them LSC and another one is NDVI. So I want to actually make a layer stack including the LSC and NDVI. Stack equals to earthengine.image.cat. The LSC and NDVI band selected. Run the stack here. We have one image with two bands. The first is the LSC, the second is NDVI. You can rename the bands through the select band first and band second identified with 0 and 1. The first band name is LSD and the second band name is NDVI. Let's run again. Now you can see the LSD and NDVI with the new names. Okay, the data is created. Now we need to convert it to the Xarray structure or array structure or multidimensional structure. This is a key point in the Earth engine. From now on, thanks to XEE library, you can convert your image collection or Earth engine images to the array structure. When you do this conversion, you will be allowed to apply machine learning, advanced machine learning and deep learning algorithm in Colab environment without any challenge. For example, here I'm gonna use the random forest to increase the spatial detail in this satellite in the thermal infrared bands, and easily I can call the random forest regressor and also do the modeling and do the validation process and get the export without any limitations. We already have without any limitations that you may face in the code editor environment and JavaScript. It is very easy to do in the Python API programming compared to what we are doing in the code editor environment or JavaScript. Okay, now make a data set or DS variable, the data set with 1 kilometer resolution. First, I need to convert a stack layer. As you know, we have different resolutions, LSC 1000 meter, NDVI 250 meter. First, I want to resample the NDVI to LSD resolution, both of them with 1 kilometer. And we want to make the model based on 1 kilometer accuracy resolution and then apply the model on actually NDVI data with 250 meter to reach the higher accuracy for the LSD. Let's see. In the first step, or to do this, we need to have two kind of data set. One of them with 1 kilometer and another one with 250 meter spatial resolution. From the XR called the open data set because we want to convert the image stack to a multi-dimensional array structure. The stack based on EE engine and CRS equals to WGS84, that here it is EPSG4326, and scale equals to 1 kilometer. EPSG unit is the degree, so we need to enter the scale based on the degree value. 1 degree equals to 100 kilometer in the square, 100 kilometers. So here 1 means 100 kilometer spatial resolution, 0.1 means 10 kilometer, 0.01 means 1 kilometer. The next is about the geometry. The next argument is about the region of interest. It is very important to bound your analysis to the ROI already defined here. So make a same data set with 250 meter spatial resolution using a new variable. Now we want to have a new data set with 250 meter pixel size XR open data set stack engine sets to EE library CRS equals to EPSG4326. The only thing the scale is the only thing that changed. So the scale equals to 00025. There it is. Sorry, 10 actually was extra, and the geometry equals to ROI. There it is. So two data set, two array, multi-dimensional array structure with different pixel size created. We want to do modeling with 1 kilometer images, and then we want to predict the higher thermal infrared resolution using 250 meter spatial resolution. Okay, now in the next step, I'm gonna show you what is the multi-dimensional structure. As you can see in the array structure or Xarray structure, you can convert your image characteristic to different dimensions. Here we have a time dimension separately, but as we have only one time, it is not multi-dimensional, so we don't want to use the time dimension in this tutorial, but the longitude and latitude, both of them are available and shows the extent of your the data. And here we have two kind of variables with different attributes, and get provided some information about each variable separately. So this is the multi-dimensional data structure, and now we want to actually make a model between NDVI and LSD using random forest regression. Make a new code first, and now we need to convert the multi-dimensional array structure to the data frame structure, because one of the advantage in the XE or Xarray structure is that we can easily convert our data to a data frame structure, do the calculation, get the result, and then visualize it with a raster or grid structure. This is actually helping us to speed up the processing instead of actually use time consuming process on spend time consuming process on raster and grid structure. So as we already had 1 kilometer, two kind of data set with different resolution. Now we want to have two kind of data frame, or one single data frame for each. Data frame for 1 kilometer data set with 1 kilometer to data frame. You can see it is very easy to do. And the next one is data frame with 250 meter and VS 250, and then two data frame just like this. Let's run, and after a few moments you can make a print from 1 kilometer data frame and see that the same multidimensional structure converted to a multi-dimensional array converted to a data frame actually with multi indices, time, longitude, and latitude. For each latitude and longitude, you have one LSD with correspond NDVI. So now this format is really suitable for analysis on for relationship analysis using machine learning algorithm, as there is not a very linear relationship between NDVI and LSD. I'm gonna use a random forest model to find the complex relationship between these two variables. Okay, now in the next step, we need to define X and Y before modeling process. From 1 kilometer data frame with 1 kilometer, so we must identify which one of them is X and which one of them is Y. So the X equals to the NDVI. X is predictor and NDVI is our predictor that we want to use to predict the Y. The Y here is the LSD. There it is. So go next, and in the next step we need to call random forest a regression model. So couple of libraries should be called here before modeling. The first one is from scalearn dot model selection. For the sampling purpose, we need to use a train and test a split function from scalearn library. The train test split allowing us to split the train and test data for X and Y. So let's run and make a new variable. Now we need to collect the train and test and split them up using Python API, using Python programming language. So write like this: xtrain, xtest, ytrain, and ytest. All of these parameters uh, will be extracted using train test split function. So couple of arguments essential here. First is identify the X and Y, and another one is the test size. How much of your data allocating to the test process. For example, I prefer, as I have a very small region, I prefer to only allocate 5% of data for the, for example, test and validation process, 0.05. 5%, but typically it is 20%, 0.2. You can change it based on your own scenario or your own references. The next argument is the random state equals to 42. So the random states ensures the same samples will be considered when you run the code again. If you run the code again, the random states ensure the same sample selected. So let's run, and now we have the train test values for the X and Y easily. So in the next step, I need to call the random forest regressor from the scalearn. Again, from scalearn ensemble import random forest regressor, just like this. Define a model as random forest regressor, and a number of estimators is very important. Typically, we allocate 100 estimator or 100 trees for the random forest method, and random states again sets to 42 as a constant value to ensure the same parameter and same samples will be used in the next run. So now we need to fit the model based on X and Y train. So model.fit X train and Y train. Let's run. Sounds something is wrong. Estimators. I think it should be estimators. Yes. Now the problem is solved and model is created. Okay. Now a model is created and we can predict the Y. So Y predicted Y equals to based on the model values do prediction for each test. So based on each test value, Y predicted. Now we want to do the validation before actually producing the final image. We want to know how much the accuracy will be in this model based on the samples and also the homogeneity in the region of interest. Okay, now we need some we need some statistical metrics that allowing us to assess the accuracy of the model based on predicted values, y predicted by comparison between predicted y and also the y already selected as the test. So now from sklearn again dot metrics this time import mean squared error and R2 score. These two parameters allowing us to calculate or do the validation easily. So now I'm gonna calculate the RMSE between predicted Y and test Y. So to do this, I need to have numpy as np next to the metrics. So RMSE sets to from numpy calculate the square root for the mean squared error between test y and predicted y. So this allowing us to understand how much is RMSE in the model's prediction. So, and the next one is R square R2 score automatically doable using R2 score function. Let's print the results. Okay, the RMSE equals to RMSE variable, print again, this time R2, there it is, R2 variable. Let's run, and here as you can see the RMSE is around 1.9 degrees Celsius and R2 equals to 69, meaning that 70% actually there is a consistent relative consistency between the predicted value and also the test value. So from now on we can apply the model on whole of the data to predict the thermal infrared image with 250 meter spatial resolution. As you remember, we had two variables. One of them was 1 kilometer that we utilized for the modeling, and model is created now. And the next one was related to a prediction procedure with 250 meter resolution. So now we need to use the second data frame with 250 to predict a new LST based on existing NDVI. So a new cell, call a new cell, and then in the data frame with 250 meter resolution, add a new column. It is predicted or sharpened LST. LST sharp equals to, so based on created model, we want to predict the new LST with 250 meter resolution based on NDVI values. Let's run 250 meter. Let's run. And now you can see a new LST column calculated or predicted based on a model. And you can easily compare the differences between these two estimations. Definitely they are not same because we did an estimate, we actually predicted a new LST based on NDVI variation that higher spatial resolution expected based on. So once the calculation or prediction is done, we need to convert our data frame from the data frame structure to the Xarray structure. So now the data set with 250 meter should be created. DF 250 meter already included LST sharpened to Xarray. It is very easy to do. 250 meter again. You can see we have a new data set with higher spatial resolution and new variable that is predicted in the data frame structure. So next, we need to do the visualization to see how much spatial detail increased in the sharpened image. So let's call matplotlib matplotlib.pyplot as plt. So now make a figure and x plt dot subplots. There it is. I need to have a plot with two columns, for example, one row, two columns, and fixed size sets to, for example, 8 and 3. plt.tight layout actually help to make enough space between each plot separately. So get ds 250 dot select the target first variable, the LST, and do the plot. Set x-axis to the longitude, y-axis to latitude, and robust to true to avoid outlier impacts on visualization process. And the next is about the color map. Color map sets to hot, for example. Do the same and remember to set the axis as we have two plots space here. The first axis space belongs to this plot. Again, do the same this time for sharpened image. LST sharp dot plot x lon y sets to latitude, robust sets to true, cmap sets to hot, x sets to x number 1. Let's run, and here you can see a detailed LST map. As you can see here, for the same range of value, you can see how much spatial detail increased in this region. Higher temperature zones highlighted with a brighter color and vice versa. The lower temperature with the darker color. So some of the words here actually mixed together. We can increase the spaces between these two plots through the width pad. equals to 2, for example. Now it is better, or even 3. And also you can change the name of each plot. For example, for the first plot, x0, set a title. This is original image, or we can set the spatial resolution 1000 meters, and x number 1 sets title. Another one is 250 meters. Let's run, and here you can compare the images with different titles that's addressing their differences in their spatial detail. So if you want to get export with high quality, just type plt.savefig, just like this, .savefig, and here the plot name is, for example, T-sharp mod output thermal sharpening with PNG format. Then the next parameter, DPI 360, BB box inches to tight. So let's run. There it is. In the left panel, here you can see the T-sharp output. Let's run, and here you will find the output in an image with a high quality. There it is. You can see the downscaled image with 250 meter resolution and the original image with 1000 meter. And this scenario is very easy to do, and even you can add more predictors. In addition to NDVI, you can add more predictors to get a higher quality and even a better accuracy in the modeling process. I hope you liked this tutorial as much as I did. The code link attached below the video in description box. You can easily find it and compare your code with mine. If the problem still exists, you can reach me out and ask your question on my YouTube channel. Please share this tutorial with other people who are interested to remote sensing studies. Thank you for your attention.